Yes, it is perfect.
Oh, good.
Yeah,
okay.
it's very good.
All right. So before I start my talk, I would like to take this opportunity to thank Professor Pastor and Professor Wei for their invitation to give the keynote lecture, to give lecture in this very nice ALERT school. I know this school for several years, and I has been following this doctoral school, and it has been a pleasure to see many quality lecture in the previous year. So it was my really great pleasure to give one of the lecture in this doctoral school this year. Now, the topic I'm going to present today is the on the SPH methods. And before I start my talk, I would like to also take this opportunity to thank my colleagues who are not here, who is currently professor in the University of Adelaide, who has been working with me for several years, and we learn from each other. And I also would like to take the opportunity to thank my former and current PhD student. They are not here, but they has been making a significant contribution to my talk. And without their excellent work, I would have not be able to progress this far in terms of advancing the SPH methods for the application in geomechanics. Now, before going to this this application here, I would like to show you this this one of the very famous disaster which occurred last year, and I believe many of us would know what is it. This has become one of the very I think I see some chat or comment. I need to check what is that. Okay, all right. This has been a very popular disaster which occurred in Brazil last year. Is basically the Tensile dam collapse, which killed more than 200 people. We have a lot of lessons learned from this event here. In particular, if you're looking at this, the report which was conducted after the collapse, you would know that the this Tensile dam here have a very well warning system put in place. But unfortunately, we was not be able to detect what was happening or to be able to predict the failure. We also have the inspection occur 1 month before the event occurs, but we was not be able to detect the failure. So the question for us here at a geotechnical engineer and as well as the academic who working in this area is how do we, what can we do to minimize this problem? And obviously, the computational methods could play a key role here. We may not be able to predict the possibility of failure, but we should be able to evaluate the impact of failure if it occurs. And for these reasons, advanced computational methods like the S methods would be a powerful tool to not only trying to predict, but also trying to evaluate the consequences of such disaster. And particle-based methods is highly suitable for this particular application, and SPH is one of them, but not only the solution. Now, so what is the SPH methods? To give you an idea of what is the SPH methods, I presented here several sort of the standard numerical methods in the geomechanics field, which was characterized into the continuum and the discontinuum numerical methods. I also classify the methods here based on their feature. For example, ranging from mesh-based, where we have the finite element methods or finite different methods, to the hybrid between mesh and particle, which belong to the class of particle finite element methods or MPM, and the mesh-free methods, which is the only methods that is require no background mesh. And on the right-hand side, you have the discontinuum methods, which is different from the continuum methods. And belong to this class, we have a discrete element methods, which is not the topic of this lecture here. And by comparing this continuum class of numerical methods that you can see here. And obviously, the SPH method is the only numerical method which require no background mass. And this is completely different compared to the particle finite elements or the MPM methods. And the other feature that you need to keep in mind that many people actually asking me, the SPH method is called particle methods, but actually some people are actually confusing SPH method and the discontinuum methods. So clearly it should be distinguished here that SPH must be or actually belong to the group of the continuum methods, where each of the particle here are actually occupies a continuum domains and carry out the field information. Now, why SPH method and how does it work? Now, in SPH, the computational domains is basically represented by set of particles, like what you can see from here. And each particle carries or occupy a given continuum domains and carry the field information. Why this one is not working here? Can I? This one is working. And then once we discretize the computational domains into another particle, we can then using an interpolation procedure to calculate the value at some particular location. Here are a couple of key advantages of the methods. Basically, it requires no background mesh and is having the Lagrangian feature, and therefore they can simulate extremely large information like what you can see here. The method itself is a non-local approach where the information calculated at some particular location are approximated based on information accelerating area. This is a couple of limitations. If you're looking at a limitation, here are a couple of limitations that you can see from the literature, which is quite interesting. Mostly in the literature, they cite these SPH methods as the methods which suffer from boundary condition or suffer from tensile instability. To be honest, when I'm looking at this literature, they actually always cite this to the paper which is 30, 40 years ago, and they try to ignore the recent progress of SPH, which I'm going to show you today and see whether we're really having this sort of the serious issue in the recent advance of SPH or not. The next question would be, why do we need to use the SPH methods? And I believe that one of the key or the main advantage of SPH methods is to bring or to simulate or to predict the field application. And here is an example where this work was conducted by one of my current postgraduate student, Edward Yang. He have done excellent work in scaling the SPH to the field scale application. And you can see here that we was able to simulate the entire the mountain in the scale of kilometers, 1,000 meter scale. And here is an example of the debris flow which occurred in the Mount Helens in Washington in 1980, which is quite popular, famous sort of a disaster, killed more than 57 people. The method itself can very well suitable for this application because it requires no background mass or no computational mass for the entire domains. And it can also be used for some other application to replace the FEM. For example, with FEM, we know the FEM is very famous for the accuracy for small deformation. But when it comes to large deformation like what we have here, the SPH would be a useful tool to predict the final runout distance. Or the methods can be also quite suitable for predicting the multiphase problem, and this is another excellent work done by one of my current PhD students who are looking at to using the SPH method to simulate the rainfall-induced load failure. And I'm going to go back to this application in the tomorrow lecture, where we discuss about how we extending the SPH methods to predict the multiphase problem. More challenging is the problem that related to fracture mechanics, and this was the work done by my former PhD student who has successfully extended the SPH methods to simulate rock fracture, both for the quasi-static and dynamic problem, which I'm going to also revisit this application tomorrow at one of the potential application of SPH. So this is a couple of very quick summary to see what is the potential of SPH method and its capability and how we actually why we are using these methods. So with this, I'm going to start my lecture, which basically I'm going to start to giving you some basic idea of what is the SPH methods. I will start with very fundamental of SPH and how we derive the fundamental equation of SPH, as well as its alternative formulation. And then I'm going to discuss some of the issue that we have been commonly that I consider as a misconception about the SPH methods. For example, some of the issue related to boundary condition. I want to show you that why we actually having or frequently cited that SPH is suffer from the boundary, or some of the stabilization techniques that has been established to stabilize the SPH methods, and what was the issue that people cited in the literature, and what are the confusion come from. And I will end my lecture with some conclusion and outlook of the methods. Now, to start with the SPH methods, this is the, for some of you who have new to these methods, probably it's a good idea to see, actually, to know these two paper which is considered at the origin of SPH methods. It was developed by Nguyen and Monahan and Lexi for astrophysics application, basically the formation of star, how to simulate the formation of star. And by the way, Professor Monahan is currently a professor at Monash University, and he's currently retired, but still quite active at Monash. So what is the SPH methods, and why do we need the SPH methods for the computational geomechanics? So to understand that, what we need to do is we need to see why do we, or what we normally do in the computational geomechanics. So for example, if you want to simulate or predict some sort of the slope failure or any problem that I presented before, what we need to do is we need to solve this what we call governing equation, which basically consists of the mass conservation equation, momentum conservation equation, and the constitutive relation. I assuming the isothermal system, so therefore I will not consider the energy equation. Now, if you're looking at this equation we have here, you can see that in the first equation, you can actually calculate the rate of the change of density with respect to divergence of velocity. And here you actually involve the spatial derivative of the density. Similarly, in the momentum equation, this equation normally used to describe the motion of particle, which nothing but the Newton's second law. This equation allows you to describe the motion of particle, okay? And again, this equation involves the spatial derivative of the stress tensor. And finally is the constitutive relation, which is basically the relationship between stress and strain, is commonly used and required to complete the governing equation. And this equation also involves the strain rate tensor, which is the spatial derivative of the velocity. Now, when you're solving this system equation in the continuum mechanics, you would need a numerical methods to approximate or to discretize this spatial derivative. And each methods have their different way to calculate or approximate this term. And the more robust method, the better when it's moving to the field scale application. And the entire idea of the SPH methods was basically built to approximate this term. And I'm going to show you how we approximate this term and what are the alternative form that we can have in the when it comes to the SPH approximation. Now, I will start with the foundation of SPH. So what is the SPH methods? To give you an idea of what is the SPH methods, first we need to consider what we call continuum fields. This is the continuum field that I consider. And this continuum field is basically represented by a set of particle or the point mass. Each point mass here is occupying a volume space and having a certain mass and carry out the field information. Now, the common question that I would ask here is, how do I calculate the continuous density field at a given location? If I want to calculate continuously density field at this location, what is that and how I do that? How do I do that? Okay. The simple way to do it obviously is to, for example, if you're looking at the particle at this location, one of the most simple ways to calculate the continuous density field at this location is to take the sum or to define a sampling volume, right? Which is basically V sub SP. And then calculate the total mass of all particle located within this volume, and then averaged by the volume. And this is the formulation, the first formulation we can use to calculate the density or the continuous density field. And you can see from this equation is the continuous density is equal to the sum of the total mass, which is the mass inside this continuous volume here, and then divide to the volume of the sampling volume. Okay, this is quite straightforward. What is the issue associated with this? If you're looking at the way we estimate the density based on this formulation, you see that this particle here and the particle there is actually close to the boundary of the sampling volume, meaning that if I extending the control volume or sampling volume, or if I shrink the sampling volume, I can end up with either exclude this particle or include this particle. This actually results in the fact that this formulation here basically will produce a very noisy density estimation, which is not ideal for the continuum mechanics. Whatever we can do from here. Now, in order to avoid this problem, what we can do is instead of taking the equal contribution of all particle mass, like what we're doing here, what we can do is we can using a sort of what we call weighting average approach, where we still define a sampling volume like what we have here, but instead of taking the equal contribution to the center particle, what we're doing now is we're taking the contribution but weighted by this kernel function, W here. This W function here will basically having a peak value, the peak value at this location, and gradually reduce at a distant increase and vanish at this location. And if we are doing this, then we will end up with a different way to estimate the density. Now the density at a given point here will be calculated by the sum of the mass inside this area, then weighted with the kernel function W. This kernel function W need to satisfy some certain condition. And in particular, if you want to remove the boundary effect here, this kernel function need to be vanished at this location. And this kernel function needs to also reach peak value at the center and gradually reduce. And this is the key idea. This equation here, we're actually giving us a better approximation compared to the previous one. Now, what we can do next from here is now we're having this equation, right? We're having this equation here, which is nothing but the estimation of the continuous density field. The next step we can do is we can actually replace this mass by the products of density and the volume. This volume here is basically the volume of the particle, okay? And then from this, what we can do next is we're replacing F by V. This is replaced by F. We're replacing by F function, and this giving us the final formulation, which is that formulation. This formulation here telling us what? This formulation here telling us that if or a few variable at any location I, for instance, can be always calculated by the sum of the information within the domain, the supporting domains, weighted with the kernel function. And this is the foundation of the SPH methods. This equation is the basic equation which can be used to derive any existing or other SPH formulation. Now, so what you're looking at here is how about the kernel function? Now, this is the fundamental SPH equation, but the accuracy of this equation needs to actually rely on the kernel function. What is the definition of kernel function, and what is the requirement of the kernel function in order to ensure that this function can reproduce the desirable results? And you can see from here that this kernel function needs to be, furthermore, to be symmetric, in order to make sure that if the particle having a same distance to the center of the sampling volume, they should have the equal contribution. It needs to be positively defined to avoid any issue associated with the negative field function. It needs to reach the peak value at the center. So basically, this is the peak value at center, and then gradually reduce. Basically, to reduce the boundary effect, it needs to reach zero at the boundary. And finally, this equation needs to ensure the total mass conservation, right? Because when we approximate the density to our entire system, you want to ensure the mass conservation equation. And these conditions are required to ensure the mass conservation. And this condition is nothing but can be basically derived from this here. So you can see now the basic SPH formulation or the foundation of the SPH methods was actually derived from the density estimation, or from the very fundamental question of how do I estimate the density of a field from a representation, a set of particles. Very, very simple. This is the key concept or the core idea of SPH. These two, with respect to the Kernel function, this is the list of conditions that need to be satisfied that we discussed previously. And there's already in the literature a number of different Kernel functions that satisfy this list of conditions. Gaussian Kernel function is one of the very popular and one of the first Kernel functions used by Monaghan's. And you can see that the red line here is actually the function of the kernel, the value of the kernel function, with reaching peak at the center and gradually reduced to 0. It first and the second derivative actually smooth, and this is very important condition. Why they need to be smooth, I'm going to explain this one later on. On the other hand, the Gaussian kernel function here actually have some limitation, because if you're looking at this kernel function, you see that they actually never reach 0. They're actually approaching 0, right? But it's never reaching 0, meaning that when you're using this Gaussian kernel function, you need to take the information of the entire computational domain into consideration, which is quite time consuming. I'm going to go back to this topic later on when we discuss about the selection of kernel function in SPH. Now, so we're talking about the SPH approximation of a function, right? So how about a gradient, right? If you normally, you know that in the momentum equation, we have the gradient of a function, but here we only have the SPH approximation of a function. Now, to obtain the SPH approximation for the gradient, what we can do is quite simple. From this fundamental equation, what we can do is we can replace this term here. Replace this term by the gradient of the function, simply replace by gradient of function. And then it ends up with this equation. This equation telling us what? The equation telling us that the gradients of a function at a given location can be calculated by the sum of gradient of the function at the neighboring particle or neighboring point, multiplied with the volume of each point and the weighting function. Very clear that this equation can be done, but it's not good, because when you approximate the gradient of a function, you actually require to calculate the gradient of the function at other location. And this you have disadvantage when you have a discontinuity function. For example, if f is discontinuity, then this approximation is no longer suitable. So what can we do to avoid this? We can do next is to basically apply the Gaussian theorem, right? The Gaussian theorem or divergence theorem in other terms, which can actually helping us to convert this equation here into this equation. Now, how to convert this, how to apply the Gaussian theorem here, please refer to my lecture notes to see the detail of derivation. I'm not going to explore here. But the key feature of this derivation is to basically convert this, to change this gradient of the function to the gradient of the kernel function. Meaning that now, if I want to estimate the gradient of a function at a given location, what I can do is I can take the sum of the value of the function, right? Now it's the value, no longer the gradient, but it's actually the value of the function within this supporting domain, but I multiply with the gradient of the kernel function. So instead of calculating the gradient of the function, now I calculating the gradient of the kernel function. And this helping a lot in the sense that when you have a function which is not continuous, okay? On the other hand, because of this feature, the kernel function needs to be smooth. So when you define a kernel function, the kernel function need to have the smooth first derivative in order to make sure this approximation work. And this is a very straightforward approach. And you can see the process that we derive here. This is the foundation of fundamental SPH equation, and this is how we end up with the SPH approximation for the gradient of the function. Very straightforward, and all starting from this foundation SPH formulation. Now, the question we would ask here, is it a good estimator? Look like the method is quite straightforward. Gradient of the function can be simply calculated by the sum of all of the function multiplied with the value here. Would this be a straightforward approach? Okay. Now, what you can comment here is, even though this equation is quite simple, it actually does not ensure the gradient of a constant field variable vanish. What does that mean? Assuming that this function here is constant, right? If it's constant value, if this function is constant value, then the gradient of this function needs to be 0. However, based from the SPH approximation here, this approximation will be different from 0. Therefore, this equation does not ensure the gradient of the function is vanished. Furthermore, from this you can see that when the particle here, this approximation is highly dependent on the uniform distribution of particle. In particular, if the particle here are highly disordered or randomly distributed, the accuracy of this estimation is very poor. So how can we improve this issue and where the source of error come from? To understand where the source of error come from, what I can do is we can, looking at this equation, what I'm going to do here is I replace this term by Fi's, and then the gradient now is simply written in this form. To understand where the issue come from, what I can do here is I can apply what I call the Taylor expansions of the function f trace. Now this Taylor expansion of function f trace here actually giving me this term. You can see that. This is the Taylor expansion up to the second order accuracy. And you can see very clear now that if you further expanding this equation, you see that now the accuracy of this approximation up to the second order accuracy is now depending on how would the SPH approximation ensure this term, these two terms. This term is supposed to be 0 in order to ensure that this guy is equal to and this guy is equal to 1, to ensure that the gradient of this one is equal to this one. Okay, so very clear based on the Taylor expansion of the function f trace. Now I can see a clear source of error. The first source of error comes from this term, and the second source of error comes from this term. And if somehow I can guarantee or I can make sure that this approximation here equal to 0 and this approximation here equal to 1, then my gradient SPH gradient approximation is represent or produce exactly value up to the second order accuracy. However, this is not always the case, because in SPH this guy never actually approaching 0 and this guy also never approaching 1. It's always having the error, and this is the main error source. The question here would be, how do I remove this error? One of the simple and straightforward approach to remove the error is to deduct the error from this function. So what I can do here is I can deduct the error. Okay, look at this. This is the way I'm going to do. I can deduct this error from the equation, and you can see from here that basically I taking this approximation, I deduct this error, which giving me that equation here. And then this actually giving me another form of SPH approximation. Now, from here you can see that instead of having the SPH approximation simply relies on the value of Fj at a neighboring particle, now by deducting the error here, I actually end up with a new formulation where the gradient of the function is actually depending on the difference between the neighboring particle and the value of function at the center of particle. And interestingly, if you're looking at this equation actually makes sure that when f equal to constant, the gradient of f is vanished. Right? It's very interesting. This equation ensure the gradient of a constant field vanish. And this is one of the most popular SPH formulation that has been commonly used in the literature. This, however, we still having, keep in mind that we still having the error here. This is the error we have not eliminated. Okay, so even though they are very popular SPH formulation, but it still suffer from this error. What else we can do from here to actually remove this error and to ensure that our SPH gradient approximation up to the second order accuracy? And to do this, what we can do next is we can again take away this error, right? Take away this error. So basically, we deduct this error and we divide to that error. Then we obtain another different equation with another quite popular SPH formulation. We can be used to obtain up to the second order accuracy of the gradient approximation of a function. So the gradient of the function now is actually a sum of the difference of value between these two normalized to the gradient of the volume of one particle within the supporting domain. Okay. Now let's see the performance of these two equations. If you look at the three equations here, this is the original SPH formulation, and if you are using this formulation to approximate the gradient of a linear function like what I wrote here, basically I'm using a function, very simple function to test f equals x plus y. And if you are using this formulation to approximate this function for this particle distribution here, so we're using a quite randomly particle distribution, and this particular distribution here is following the Voronoi distribution, random particle. And you can see that the prediction of this function are very noisy, right? Very noisy and not accurate at all. Now, however, if you actually involve the second equation, which we derive by remove the first error source, you can see now that this equation produce quite good result for the area that is inside this domain, but they actually suffer from a low accuracy at the boundary. This is obvious because when the SPH approximation come to this place, come to the boundary, you don't have particle at the boundary area, and as a result, you actually the value are dropped at the boundary. Okay. However, if you actually using the last equation that we discussed here, the last equation that we actually normalize with the sum, which is this equation there. This is the equation we discussed. We normalize with this term. Now, with this equation, we can actually produce quite nice prediction of the gradient of the function. Now we can exactly, if you're taking gradient of this function, you actually produce the value of 1, and this function produce exactly result of 1 for a very random particle distribution right here. And you can see that starting from original SPH equation, we can using a couple of different transformations to obtain a good operator, SPH operator. But keep in mind that the tricky thing in SPH is the good operator may not be always a good operator. Right? The good SPH operator here may become the best one later on. Okay, so I'm going to discuss and explore some of this later on. Right. So this is related to the gradient of the SPH. So far we have discussed how we obtain the SPH approximation for a function, how we obtain the SPH approximation for the gradient of the function, and how we get rid of the error of the function to obtain the high accuracy up to the second order for a gradient of a function, right? Now let's see how we actually apply this method to the geomechanics. Now with the aspect within the geomechanics discipline, there's a lot of research has been conducted back to 1990, but perhaps two of the very popular paper, very highly cited paper was the one that I listed here, each of which actually using a quite different approach. And for deep integrated by Professor Ambassador will be presented in the tomorrow lecture. But today I'm going to more or less focus on the framework that we presented in this first paper. Now, when it comes to a geomechanic application, what you can see here is, again, in geomechanics, we need to use the continuity equation, right? We need to use the continuity equation, and we have the mass conservation equation. The mass conservation equation here allows us to calculate density change or the void density change, right? Or porosity change. We have the momentum equation to describe the motion of the particle, like what we can see here. And we have a constipulation to describe the relationship between stress and strain. Now, what we're doing now is we're going to use the SPH approximation equation that we adopted in the previous section to approximate this term, all of this, right? But then we're going to focus more on the capability or the issue associated with the information, okay? Now we start with the mass conservation equation. This is one of the traditional way to obtain the mass conservation equation. And you can see from here, this is how we establish the density chain, which is basically calculated from a divergence of velocity. And this is the term that we need to approximate, or we need to discretize, okay? Now, what we can do here is we can actually, using the SPH approximation, and this is again, we're using this, we start with this SPH approximation first, right? What we can do is we obtain this equation, right? We obtain this equation here, very simple. We basically replacing this F, right? We're replacing this one for that one, right? Or replacing F by V. Then we obtain this equation of the continuity equation. And the continuity equation now can be calculated by the density of the particle itself multiplied with the sum of the dot products between the velocity and the gradient of the kernel function. This equation is quite straightforward, but it's actually having the similar issue like what we discussed previously. They actually produce non-smooth divergent velocity operator because of the issue when we have a constant velocity field. This approximation does not guarantee that the constant velocity field vanish, and as a result, we are having this sort of problem, and therefore these equations are not commonly used in the literature. And the other option are to address this problem. What we can do next is we're using a better SPH operator that we discussed previously, where now if we're replacing F by V, we obtain this equation. And again, now the density change, it actually relies or depending on the relative velocity between two particles when you are actually calculating or approximating the value for this particular function. This equation giving you a better SPH approximation, and it's produced quite smooth divergence of velocity, right? Obviously, if you have a constant velocity field, you can obtain the exact solution like what you have here. And keep in mind that the gradient or function here have to be normalized like what we discussed before to remove both the first and second error source, okay? Now, this equation obviously is the good one, right? But what we can see here is we actually deriving the mass conservation or continuity equation following the traditional way. And this is the strong form of the mass conservation equation. Within the SPH context, we actually can arise at a very similar equation without using the traditional approach that I'm going to discuss later on. And this is the comparison between two equations. The first equation, which is not very popular, and the issue is due to the fact that this density, this SPH approximation, does not guarantee the constant field function is vanished, and this operator actually have to remove all the first and second source of error in the SPH operator, and as a result, this equation can reproduce exact the density change that what we require for the simulation. Now, what we have done so far is we're following the traditional approach to derive this equation. Apart from this, and perhaps one of the most interesting features of SPH is I don't need the traditional continuity equation, but I can still find a different way to derive the equation. And what I'm going to show you now is quite interesting. So in the early slide, I start with this formulation. Now, in the early slide, I actually trying to show you how we establish the SPH equation and how we establish or estimate a density at a given location. Right? This is the very fundamental SPH equation. So what this equation is, if you want to calculate the density of this location, all you need to do is to calculate the sum of the mass within the sampling volume, multiply or weight this with the Kernel function, right? This is the equation I showed at the beginning. Now, what I can do from here is, I can actually taking the time derivative of this function. If I'm taking the time derivative, right, the time derivative of this function, I can immediately obtain this equation. So you can see that starting from a density estimation, taking the time derivative of this equation, end up with a SPH approximation for a continuity equation. This equation here actually take into account, or having an extra terms here, which actually take into account the variation of this smoothing length, right? This smoothing length here. So, with meaning that if I have less particle, I need to expanding this supporting domains to accommodate more particle, or if I have more particle, I need to shrink this smoothing length to make sure that my calculation is correct. And you can see from here, it's quite interesting feature is this density approximation can be used to derive the continuity equation, which can automatically adjust depending on the information we are given. Now, if h here, on the other hand, is set to be constant, then this guy equal to 1, with meaning that its equation is go back to original equation. So this is another interesting feature of SPH. I can actually ignore all of the continuum mechanics. I can still derive the continuity equation based on this density estimator. Right? And then the same concept was also applied to derive the motion equation, but I'm not going to explore in this lecture. Now this is now the quite interesting concept of SPH. So you can see the conclusion here is the time derivative of the density estimation actually giving us a smooth divergence of velocity operator, or can giving us the continuity equation, which is quite a nice feature of the SPH. Now, so how about the momentum equation? Similar to the mass conservation equation, in the momentum conservation equation, which is basically the Newton's second law. Here you have the mass per volume, unit volume multiplied with acceleration, and here you have internal force, and this is the external force. So what you need to do now is you need to approximate this term because it's actually the spatial derivative of the stress profile. What we can do is we can, again, using a very good SPH operator. This is so far we have established that this formulation is a good formulation because they actually produce the correct SPH approximation for the gradient approximation. And therefore, I name this one as a good SPH operator. And if we are using this good SPH operator to approximate the momentum equation, we end up with this equation. What does it mean by this equation? This equation telling you that now you can actually calculate the acceleration, and this is the mass per unit volume based on stress difference. Right? This is the momentum equation that we expected after employing a good SPH operator here. What happening is, if you're looking at the equation itself, you can see that this is the force. This is the force acting on particle I, or this is the force acting on particle I. And very clear from the equation is the force acting on the particle I is different from the force acting on particle J. Or in other words, when you have the particle I approaching the particle J, right? Particle J, the force produced by particle J to particle I is actually different from the force produced by the particle J acting on a particle I. Meaning that these equations are actually does not conserve the linear and angular momentum, right? Very clear, this operator telling you that the force felt by particle I are different from the force felt by particle J when they are approaching each other. Or very simple term, they do not conserve the linear and angular momentum. What is the problem of this? If you want to see the problem, here's a problem. What we're doing here is we actually setting up I think I hear some background noise from, okay. Right, sorry. Okay. So what we're doing here is we're setting up a simulation for this particular problem where we have initially uniform distribution of particle, and each particle here actually attracts to a random stress profile. Right? We're giving this random stress profile to each particle, and you can see that if we are using this formulation to approximate or to calculate, if we're using this equation to calculate the motion of this particle here, and keep in mind that the particle in the boundary here outside remain fixed, and the particle inside this area we are allowed to have the free motion following this momentum equation. Now, if we're using this equation, we see very clear that this equation will end up with this highly unstable solution, and you can see that finally the particles are getting clumping to each other, and they even blow up at the end because of the issue related to linear and angular momentum conservation equation. And very clear now that you can see we actually using a good SPH operator to approximate the governing equation, but then we end up with these results, meaning that the good SPH operator now become a best choice for a momentum equation, right? So what we can do, or what can we do to fix this problem? Now, to fix this problem, what I can do is we can start like this. So we have this is the original momentum equation. Now what I can do is we add this term to the momentum equation. Now you can see that when we add this term to the momentum equation, this guy actually equal to 0 because gradient of 1 is equal to 0. So we're actually adding 0 to the momentum equation. And at the results, next what we're going to do is we're going to using a bad SPH operator. This is the best one compared to this one. This is the good one, right? But this is the best one. We're going to use the best one, right? And then by using this, we end up with this equation. Quite interesting, even though we are using the bad SPH operator, but we end up with quite nice governing equation or momentum equation. We conserve both linear and angular momentums. It's quite interesting. The reason is if you have two particles now approaching each other, they both actually feeling the same amount of force acting on each particle in the pairs y minor, and that's why they actually conserve both linear and angular momentum. And you can refer to my lecture notes to see how we actually prove that this equation conserves both linear and angular momentum. And how about its performance? This is the demonstration of its performance, right? What we're doing here is very similar to previous. What we're doing here is we again create a continuum domain with a uniform initial particle distribution, and we fix the particle at the boundary or outer domain here, and we allow the particle inside domain here to move freely. And to activate the motion, what we're doing here is we assign an initial random stress distribution to this domain. And you can see that by using this form of equation, can somebody, I think there's somebody, and there's some background noise. Maybe you can mute that applicant. Okay, I think I can mute them. All right. Now, what we're doing here is with you can see here with this vast SPH operator, it's actually become a very good choice for a momentum equation because they actually producing a quite nice momentum equation that conserves both linear and angular momentum, which is quite interesting feature. And now you see that with various options that I have showed you previously, the SPH have quite flexible choice, and sometimes the good operator may become the best one, and sometimes the best one may become very useful. So what I mean here is in SPH, we need to understand very clearly the key feature of each approximation and make sure we are using this operator correctly in order to obtain a correct solution. Now, in summary, this is a couple of the SPH formulation that we can obtain based on the derivation we have previously. Now you can see here, with regard to the mass conservation equation, this is the original form of SPH approximation that we can obtain. This equation has been most commonly used in astrophysics and is suitable for astrophysics. But unfortunately, for our application, they are not suitable because if you are using this equation here to approximate the density at this particular location, the density would be significantly dropped. which will not result in the correct result. On the other hand, if you're using this equation, the density change is actually more or less depending on the velocity difference at this particular location, and therefore they can produce a better results. However, this formulation here is only suitable for a homogeneous slope, a homogeneous material, because the density or the summation, the density change now, it actually calculated based on the mass. So if you're looking at the approximation, this density at I is actually depending on the mass of change here, right? So if you're having a non-homogeneous soil profile, like what you have here, soil 1 and soil 2, with significant different density, meaning that when you calculate the density at this location, you would need to take the mass of soil 1 to calculate the mass of soil 2. Therefore, this equation is not good for non-homogeneous slope. Alternatively, you can have a different equation here, which actually only relies on the volume. So you have here density change equal to the density of particle itself multiplied with the volume, right? The volume, not the mass. This one you multiply with the mass, but this one you multiply with the volume. So this is the key difference. This equation is suitable for the multi-layer problem where you have the non-homogeneous slope with highly different density profile. If that is the case, this equation needs to be used. On the other hand, when you are using a homogeneous slope like what you have here, you can use this equation. Okay, this is a couple of conclusions. And in terms of the momentums, this is the only equation that we should not use because this equation does not conserve the momentum. On the other hand, we can have an alternative form of the momentum equation which actually conserve exactly the linear and angular momentum. Okay, now so that is the starting point of SPH and how we're actually using the SPH to approximate the mass and then and the momentum conservation equation. Next is coming to the selection of the kernel function, because you can see what we done previously. We actually require selection of the kernel function, right? This we have not actually discussed in depth. Now what I'm going to do next is I'm going to discuss how do we actually select a suitable kernel function. Then there's a lot of issue actually associated with the selection of kernel function when it's coming to the SPH application to the engineering of engineering. And this actually the source of the confusion that we may have. So this is the condition of the kernel function that you might remember I presented in the first couple of slides when we're talking about the SPH approximation for density field. And very clear that when you're using the SPH, the kernel function need to be symmetric and positive, like we discussed previously, to make sure that the particle with the same distance have the equal contribution. And then we also need to make sure that they have the smooth derivative and having compact support domain to make sure that they are not just taking on our entire domain into consideration. And it needs to be ensure the mass are conserved. This is the key idea. And in the literature, there is already a number of kernel function that actually satisfy this condition. For example, you can use either Gaussian kernel function, cubic spline, and Nguyen C2 kernel function. These are the three most popular kernel functions that is commonly used in the literature. And they are very similar, except the Gaussian kernel function, the cubic spline, and the Nguyen kernel function having a very compacted support domain. So basically, the kernel cut off at this location. The Gaussian is the only one that extends infinite to the entire computational domains. And the other good thing of these three kernel functions that they all having a smooth first derivative, right? This is very important because when you actually approximate a gradient of a function, you actually require the gradient of the W function. Then that's why you need a smooth first derivative of the kernel function. However, this selection of the kernel function is also causing a lot of issue, and this is the source of the common misconception of SPH in the literature. Now, if you're reading a lot of paper in the literature, you may always read or you may find that most of paper actually cited to SPH as the method suffer from tensile instability or from tensile instability. But what happening here is most of those actually cited to very old paper or cited to the paper who actually misuse of the kernel function. I'm going to show you what is the problem there. What I want to say here is, even though we're having a number of choice of the kernel function available in the literature, but the wrong choice of the kernel function will lead to the issue that I call pairing instability. And this pairing instability is very similar to the zero energy modes in the finite element or some other numerical methods. And this is often cited as the SPH instability issue, which is quite a misunderstanding, all right, conceptual. What happened is, okay, now looking at this one, this is an example of using a cubic SPLI function. This is the cubic SPLI function, right? The Pro one here, and this is the results of the SPH simulation for against initially uniform distribution of particle with a uniform pressure distribution. And for each of the simulation here, we are using a cubic SPLI function, but the supporting domain or the kernel size are different. For the first one, the size of the kernel is following this condition, which basically is quite small. When you actually, the middle one are relatively large, right? Which is we're extending this supporting domain. And the last one here is extremely large, right? We extend further the supporting domain. What does it mean here is, when we're extending this domain, we actually forcing the kernel to take more particle. So if you're looking at the first one here, you may have around 10 or 15 particle to contribute to the center particle. This one you may have a double, on this one you may have a triple, right? So this means that you increase or you force the kernel function to take more particle, and as a result, you actually end up with the issue here. If you don't actually, if you're having a suitable number of particle, the simulation remains stable. If you force the kernel function to take more particle, you actually causing what they call instability or what they call pairing instability, where the particle seem to actually forming a clump like this. This is the worst scenario, where you actually having a very large supporting domains and is actually causing this problem. Unfortunately, this problem here is actually often cited as instability, and they actually using this condition to cite it that SPH is having the problem, but they don't using this condition. Meaning that if you actually using a suitable kernel function, then you don't have that sort of instability problem, okay? So what I'm going to do, I'm going to show you this sort of application later on. Now, the conclusion from this test is the SPH particle form the clump here due to the wrong use of the kernel function. Keep it in mind. What you can do is, where is the source of it come from, right? What is the source of instability? Where does it come from, right? Now, what you can do now is we're looking at, first we need to keep in mind that each kernel function could only accommodate a certain number of particles. So basically, you should not try to force the kernel function to take more particle, because if you force the kernel function to take more particle, it ends up to the situation that I showed you in the previous slide, where the particle are actually forming the clump. This is the first case. Second, if you're looking at the kernel function, you see that this is the motion equation, right? This is basically this equation show you how the motion of particle basically calculated by the product of the stress multiplied with the gradient of the kernel function. Now, what happening here is, if you're looking at the gradient of the kernel function here, you see this is the Gaussian kernel function, and this is the gradient of the kernel function. And you can see that the gradient of kernel function actually approaching zero, right? When the distance reduces, they are approaching zero at this location, meaning that each kernel function have what we call inflection point corresponding to the zero kernel gradient, this location here, right? So each kernel function have zero gradient. So when you're having two particles actually getting very close to each other, this W, gradient of W is zero, meaning that the entire term here is also zero. And as a result, the particle, these two particles would not gain enough repulsive force, causing the clumping issue that you see in the previous slide. This is the second issue. And however, if we actually have the appropriate choice of the kernel function, we can completely remove this. Right? I'm going to show you the example. This is an example of what we can do to remove this error. Now, in this particular case here, I show you three examples with the same simulation setup that we did previously. Initially, we have a uniform particle distribution, and we're using three different Gaussian kernel functions, which is the popular kernel function that you can see here, Gaussian, cubic, and Nguyen kernels. Each of which we using a different number of particles, or we forcing the kernel to taking a different level of the particle, right? This one, the last column here, showing that all the kernel need to take a large number of particles in the calculation. And you can see from here, that now with the Gaussian kernel, when the number of particles are enough, right? When the number of particles are within this range, or even with the cubic SPH function, you don't have any problem. But when you actually taking the number of particles to be large enough, or you force the kernel function to take more particles, you start creating the issue related to pairing instability, like what you can see from here, right? Gaussian start to producing the issue when they actually forcing taking this mass. Cubic SPH function immediately start to producing the pairing instability when these two are actually equal to 3. On the other hand, if you're looking at the Nguyen kernel, you don't have this problem, more or less. Regardless of how many particles you actually forcing the Nguyen kernel to take, they are always stay stable, and you don't have the problem of pairing instability. This actually totally not occur in the Nguyen kernel function. Now, why is that? This is actually can be explained further by a research conducted by Daniel and Ally in 2012, which show that of the three kernel functions, the only Nguyen kernel function is the one that produce the transformation, the Fourier transformation are actually positive. Or in other words, what he's saying here is that any kernel function whose Fourier transformation is negative for some wave vector will trigger the pairing instability. In these three kernel function, Nguyen kernel function is the only one that are not suffer from this negative Fourier transformation, and therefore is capable of removing the pairing instability issue. Now, the key message I want to deliver from this slide or this information is, if we actually using a suitable kernel function with a suitable supporting size, we don't have a problem with the pairing instability. This is the, and as a result, in SPS, it's not because of SP instability, but it's because of the wrong choice of kernel function causing instability. And this has been a common misconception in the literature, which telling the SPS having instability problem. Now, the issue that they might actually mention in the literature, I believe, is actually related to what we call tensile instability. This is a different issue compared to the pairing instability. Tensile instability is in SPS is the issue that basically occurs due to the positive stress. Now, positive causing attraction force. That means when you have two particles with positive stress, you actually causing the attraction force like that. We're causing two particles moving close to each other. It's very similar to the pairing instability, but it's not pairing instability. It needs to be distinguished from the pairing instability issue, because the pairing instability issue was caused by the wrong use of kernel function, while the tensile instability issue is actually caused by the positive stress with causing attraction force. These two issues are totally different, right? But what people are referring in the literature are the tensile instability. And unfortunately, the tensile instability are very common in any particle or methods, not just SPH. I'm going to show you example later on. It actually occurs in all other methods, but the question is whether we're taking it serious or not. And the other source of this, I believe, the misconception is come from this very highly cited paper. Now, this very highly cited paper was conducted in 1995 by Swego. He basically using the cubic SPLI function, which is quite and analyzed the tensile instability problem, tensile instability, not pairing instability. Keep that in mind. He analyzed the tensile instability problem, and he established the condition. This is the condition. The condition saying that if the product of the stress tensor multiplied with the second order derivative of the kernel function less than 0, then the SPH simulation would have would become or suffer from instability issue. Now, what happened to this? If you're looking at this one, this is the second order gradient. Now, this is the first gradient of the function, and this is the distance, right? It's a distance. This is the first gradient, and you can see this is the for any kernel function you should having this sort of first gradient, right? Distribution. And this second gradient, second order gradient here is nothing but the slope of this guy, right? The slope of the first derivative, right? The second gradient here. And this condition telling you that the SPH methods are actually unconditionally unstable. That means it's always unstable, right? Regardless of whether you have positive or negative stress, this condition is always satisfied in these two domains, meaning that they're unconditionally unstable, right? But this condition is totally wrong, because what we analyzed previously, that if we're having a suitable kernel function, we can completely avoid the tensile instability problem. So what happened is, when Swego analyzed this problem here, he did not recognize the issue of pairing instability, or he actually combined these two together to establish this condition, right? So when you cite it to this paper, you need to make sure you understand that what you are citing. There you are actually citing to the tensile instability problem, or you actually citing to the pairing instability problem, or keep that in mind, okay? If you're sharing to the pairing instability problem, then it's wrong, okay? Now, so what is actually the tensile instability, and how does that actually manifest in the geomechanics? This is the issue that I have showed in the early SPH application. Now, this is the issue of what we call tensile instability in SPH, right? Or in SPH application to geomechanics. What happened is, when you have the tensile instability problem, you're seeing this sort of behavior. The particles are actually separate or become fragment, fracture or fragmentation. That's what you can see from here. And this issue, because it's only happen or occur when you have the stress less than 0, and therefore this case, this tensile instability should only occur in the cohesive soil. They should not occur in the non-cohesive soil, right? This is a very, very important sort of conclusion we need to remember. For example, if you're looking at a soil like Drucker-Prager cohesive model, and this is the mean stress or the I1 first invariant stress tensor, and this is the derivative stress, and this is the U condition, right? You're looking at the U function, you can see that for cohesive soil, you actually have the tensile zone. This is the area that causing this instability. On the other hand, if you have a non-cohesive soil, you don't have this tensile area. You don't have this area. And that result, for non-cohesive soil, you should not have any tensile instability problem. So with respect to the tensile instability issue that has been commonly reported in literature, they should not occur in the granular soil. They should only occur in the cohesive soil. And we can remove it, okay? We can remove it totally. I'm going to show you how we're going to remove it later on. Now, so how are we going to remove it? Now, the next question here, quite interesting question, which is, do these issues only occur in SPH, right? So you're looking at the problem that we showed previously. This is the instability issue, right? How about other methods that I'm going to show you? This is the question, and the answer is no, because the same problem occurs in different particle methods. For example, here's an example of MPM simulation of the granular material, and you see that there is an issue of particle fragmentation, there's issue of particle clumping, and also issue of particle clumping here. And this actually a very common issue in particle methods, not just in SPS. But the problem is, in other methods, they actually did not consider this as a tensile instability, all right? But in SPS, we do consider this as an issue, and as a result, we would need some specific treatment to avoid this sort of problem here. So what can we do to avoid this sort of problem? So first, we need to avoid this sort of problem, we need to make sure that we implement the concept model correctly. Because this, without implement concept model correctly, we always create the issue. For example, you create a positive stress in a granular soil. This is the issue causing the instability problem, right? And secondly, if you're having the concept model that have the tensile region, and there's no way you can avoid the tensile region, then what we can do, or the simplest way to do, is to using what we call the artificial stress. And the artificial stress is working in a very simple way. What we do is actually we're adding an additional term to the momentum equation. This is the momentum equation. This is the additional term adding to the momentum equation. And one of the most commonly used artificial stress term was proposed by Monahan in 2005. I'm not providing the detailed formulation here. You can refer to my lecture note to see the detailed equation. But the key idea of this term is actually produce the repulsive force between two particles when they are approaching each other, right? When they are approaching each other. And this force here is only activated in this zone. They should not be activated in this zone, right? In this zone where you have no tensile instability, then this force should not be activated. But when you actually encounter the area with the tensile instability or tensile stress, then you should actually include this term. Alternative to this, right? Alternative to this, you can also using what they call the tension cutoff, which is also commonly used in the concept modeling. But that's another issue I'm not going to discuss here. But assuming that I'm not going to do any tension cutoff, and assuming that I need to avoid the issue associated with the tensile instability, I can simply adding this term into the governing equation, which here actually showing you it's quite straightforward to handle this sort of problem. This is an example of how the artificial stress work, and this is the case where we're modeling the elastic material, and you can see that even with the negative stress that we have on this region here, even with the negative stress, we can still actually be able to simulate the behavior of the solid beam undergo significant bending deformation. Or on the right hand side here, you see the simulation of two elastic bone collide in order, and the simulation still remain very stable with this artificial viscosity term. When it comes to the soil, now we can actually totally remove the fragmentation that I discussed previously, and you can see this problem here now can be totally removed from here by adding this artificial stress. On the other hand, for the non-cohesive soil, we don't need to do anything, right? The concept model, with the correctly implement of concept model in SPS, we should be able to obtain a correct result. And this is the issue related to instability problem. All right, now the next issue that I want to discuss here is related to the boundary condition. Now, this is another interesting, what I call as a misconception in the literature. We're always telling that the SPS methods have the issue with the boundary condition. And to be honest, again, most of these papers are cited or quoted to a wrong source. The question here is, do we really have the issue with the issue? Do we really have the boundary issue with the SPS methods? And where is this misconception come from? This is the interesting issue I actually figure out since I'm doing the SPS methods. Now, what you are seeing here is on this video here showing that the original of SPS, the SPS method was originally invented for astrophysics application, which basically simulating the collision of two stars, like what you can see from here. And in this particular application in astrophysics, you don't need the boundary condition because the particle truncation actually is a good feature of SPH. And therefore, here, within this astrophysics application, no boundary condition is required, right? However, when you actually bring the SPH methods to engineering application, we need a boundary condition, just like any other methods. Finite elements, particle finite elements, and any other methods, MPM, and so on, are all require boundary condition. For example, like what you have here with the finite element method, we need a special condition to impose the fixed boundary condition. We need also the boundary condition to impose the freeloader or the free surface boundary condition, or even some sort of the loading condition that we are imposed on the finite element mass. We still need the boundary condition. So what I'm saying here is any other numerical methods would require the boundary condition. And SPS, when it comes into engineering application, we also need a boundary condition. So how do we actually handle a boundary condition, and what type of boundary condition are required? Now, within the geomechanics context, what we would need is we would need a roller boundary condition. This is a roller boundary condition, right? With basically the free slip boundary condition. We also need the fully fixed boundary condition, and this is the fully fixed boundary condition, basically to make sure that the particle or the node at this location are not undergo any deformation with our zero velocity, or we need a symmetric boundary condition. Perhaps one of the most difficult boundary condition is the confining stress boundary condition, which is particularly this application here, where in the finite element methods, you would need to apply a constant confining stress at the outer particle here, outer node in the finite elements, or one of this location here. And you also need to ensure that this confining stress actually perpendicular to the boundary when the boundary gets deformed. And this is perhaps one of the most difficult boundary conditions that we're talking about. For the other boundary condition here, it's quite straightforward. So in SPS, to model this boundary condition, what we can do is we can using a very quite straightforward approach as well. For example, this is an application when we apply the SPS to model slope failure. And you can see from here that when the SPS approximation, or when the particle come close to the boundary, the kernel actually was truncated because you have no particle outside the boundary. And this actually affecting the SPS approximation at the solid boundary. So what you can do here is we can actually using what we call virtual particle or fixed boundary particle. The idea is to place a number of layer particle outside the boundary domains to compensate this truncation error. And then this particle need to having some certain property or condition to impose the required boundary condition. For example, this particle here, fixed particle, need to have to carry a similar property to the adjacent particle here to ensure a smooth SPS summation. This particle is also motionless. I should not and carry a virtual velocity to impose the required boundary condition. For example, if you want to impose the zero velocity here, then this particle should carry negative value or opposite velocity to this particle, and so on. We also need the stress. This particle here also need to carry stress, and this is a special condition that we need to take into consideration. So what I want to say is, it's quite straightforward. If you want to model a solid boundary, what you can do is you can using a boundary particle to represent the boundary and impose a required boundary condition on this boundary particle. Now here is an example of how we actually impose the required boundary condition. For example, if you want to model the fully fixed boundary condition, you can calculate, you can extrapolate, right? You can calculate the velocity at this location here by extrapolate the velocity of inside particle and assign the negative value to that velocity, right? Or the stress tensor can be simply calculated by extrapolate the information from the interior particle. This formulation here telling you that the stress at this particle here, at the boundary particle, can be only calculated from the stress of the real particle inside the domain. This is the whole idea. Okay. So this is how we apply the fully fixed boundary condition. We can also impose the free roller boundary condition. This is the free roller boundary condition, where instead of having a reverse sign of velocity, now we need to distinguish between the normal velocity and the tangent velocity. So for example, if you have the boundary condition here, you need to have a normal vector and the tangent vector. This is probably the issue that you might think is difficult, but in SPS it's not, because this normal vector here can be directly calculated from the SPS approximation of the gradient of the kernel function. For every particle on the boundary, like what you can see here in this location, if you calculate the SPS summation of the gradient of the particle with respect to the boundary particle, you would get the normal and tangent vector of this particular location. So this, again, the boundary condition, the velocity condition are quite straightforwardly applied. The difficult thing, and here is an example of what we can do with all of these things related to boundary condition. For example, we have been showing that we can simulate the bearing capacity problem using the virtual boundary particle here without any problem. We can actually model soil structure interaction like what you can see from here, where you can just using the boundary particle to model interaction between soil and solid. Or here is the direct sailboat test, where we're actually using the boundary particle to model the solid boundary. Or even in this example here, we actually using we impose or prescribe the stress on the particle that is located right on the surface, which is very similar to FEM, and we can still exactly obtain what we want to simulate. So in other words, we don't have any issue with the boundary condition similar to other methods. We can use, or we can develop any some sort of the required boundary condition for SPS. One of perhaps the most difficult boundary condition that we may need to keep an eye is the stress boundary condition, and this is the case where you need to looking at how these sort of boundary conditions are imposed. Now, this is an example of the finite element simulation, and these experimental results. Obviously, in FEM, you can simply select the point at this particle location, impose the confining stress, and ask the software to do whatever they do to impose the confining stress. But when it comes to extremely large deformation, FEM will not capable of simulating this problem, right? So when we're talking about the boundary condition, we need to also put in the right context. FEM is good for small deformation. SPS, we can using exactly the same boundary condition for small deformation. But if you want to simulate this problem, we need to using a special ways, and how we actually doing this. So what we can do now is, in SPS, there's a couple of options available. We can actually first option is to create a boundary particle to impose the confining stress. But this is obviously not a good condition, not good ways, because it would be very complex to create a boundary particle right here. The other way to do is to follow the finite element methods to select the particle on the boundary and impose the required stress. And it's totally fine to do this, and it's work very well. But it's only suitable for small deformation, right? Similar to FEM. You can use exactly the same approach like FEM to impose the stress on the boundary, but it's only work for small deformation. What we want to do is we want to aim for something that's more advanced, something like the experiments, something like what we show in this video here, where extremely large deformation can be carried out by SPS, and this is why we need to require the SPS method. So how do we do? This is the approach we have been achieved very recently and published last year. What we're doing here is, if you're assuming you consider the continuum volume here. By the way, do we need a break? Manolo, we continue or we need a break?
As you wish. I mean, we still have until, I think it was, let me check, 11:20 more or less. So if you wish to make a break, that would be okay. If not, we can continue because it is more or less 35 minutes left. But anyway, we are going to have also a break at 11:12 or something like 10 minutes.
I can continue. It's up to you.
You choose, okay.
Yeah, just like Manolo just said, maybe only 35 minutes left, so you just maybe just pull it through. Right?
Okay, okay, then I will go ahead. Yeah.
Yeah.
Yeah. Okay. Yeah. Okay. So this is the. I'm going to show you how we develop the required confining stress boundary condition for SPS. So what we're doing here is we consider a continuum body, basically subjected to a confining stress, which is a constant confining stress, sigma sub c on the surface, right? And all we do in this approach is to add an additional term into the momentum equation of SPS particle, and we need to design this term in such a way that it always produce a constant confining stress to the outer particle or to a particle that is located on the boundary, and this is the key idea. Now, the approach we are doing here is what we do is we represent this continuum body by a set of particles, like what we have in SPS. And then we assign initial constant stress, sigma 6 sub c, to all particle. And then for every particle, we're using this equation, meaning that this equation actually in SPS would produce this term, right? If you're having additional sigma c to every particle, they actually add up some component to this equation. Now this is having a different form, but this is the term we're adding into the momentum equation. What we want to prove now is this equation, or this term here will produce a constant confining stress on the boundary regardless of how the particle deform. Okay, so how does it work? Now we're starting from this term. We're looking at this is the term we added into the momentum equation, and what you can see that this term can be actually rewrite in the integral form. It's very clear here. This summation can be replaced by the integral, like what we have here. Okay. Now, what happened to this term is, what we can do is now we can further expanding this term by adding this component and take away that component. It's very simple, right? So basically we're adding nothing to the equation, and then we end up with this equation. This equation, we just rearrange the equation here. Adding this term, this becomes 2 sigma ci. Take away this term, now it becomes sigma j minus sigma ci. Now these equations are exactly the same. If you're looking at this equation, you would see that, you would see what? You would see that this term here, because we actually, every particle have a constant confining stress, and as a result, this term are vanished across the computational domains, right? And as a result, when you're having this term, you actually getting to this. This is the only term we have in that equation. Further from this, what you can do is you're looking at this. This is the volume integral, right? This is a volume integral. This is a volume. We can using the divergence theorem to basically convert the volume integral into the surface integral, right? So this is the term we basically obtained by the Gaussian theorem or the divergence theorem. Now we apply this term into this domain. What you can see is this term here, W function, this W function are symmetric, right? We have symmetric W function, and as a result, for any integral of a closed surface, this term is vanished for a closed surface, right? Meaning that these terms vanish for any integral inside the domain, but not at this location. This location, they are not vanished because this integral are not a closed surface, right? So what I can do next is for a surface integral here, when it comes to this location, right? It comes to this location, this surface integral can be replaced by the sum of this integral inside domain here plus with the outside integral, which is this term and that term. Okay, now you see that again for this term here, they actually forming a closed surface. And as a result, this term vanishes. But this term is not, because they are open surface. The other one is open surface, which is basically that surface here. And as a result, you see that this one vanishes, but this one is not, right? If you're looking at this one here, they actually equal to the minus of stress, right? Stress here, multiply with the integral of this one here, right? Of this area, meaning that this one acting at a confining stress. So you can see this term that we added into the Goldman equation, eventually producing the confining stress, regardless of how the particle deform. And this is quite interesting. So we don't actually doing most complicated things. What we only do is we assign an initial constant stress to all particle inside and also on the boundary. And then we're using this equation to calculate the particle motion. And if this is the case, we're going to automatically produce a constant confining stress acting on the boundary of particle. And this all we do here is we actually making use of the kernel truncation property of SPH to impose the confining stress condition. So how does it work? This is an example of what we're doing here is to prove that how it works here. What we do is we consider a continuum domains like what we see here. We can represent it by, again, SPH particle. And we want to assign, we want to simulate this problem under a confining stress of 10 kPa. So what we did is we impose, initially we're giving all the particle here with a constant stress sigma c at 10 kPa on top of the stress that the particle would have. Right? This is the on top of stress a particle would have. And then we're using this formulation. And here is the result that you can see. You can see that now, after conducting the simulation using this equation, we can actually obtain a quite good, right? This is the expected confining stress that we obtain. For this case, we did not actually giving the initial 10 kPa to every particle, but we only giving to the outer. For this case, we did not actually assign the initial stress condition, but for this case, we assigned the initial stress condition. And you can see that for all cases, we actually obtain exactly the required confining stress condition. And also this figure here showing you how actually the confining vector apply on the boundary of particle. So it actually normal to the surface boundary. So this is a very simple test. And then we bring this one to a very complicated test where we're looking at a triaxial problem. So we try to simulate this problem. It is again a triaxial test where we impose a given confining stress of 150 kPa to all whole particle, and then we're sharing the soil under the triaxial loading path. Right? We're sharing the soil under the triaxial loading path that we have here. And then what we're doing here is we measure the stress loading path, and you can see that this is the global triaxial loading path, which is basically following the triaxial loading path condition. And you can see that when the sample undergoes small deformation, we actually obtain quite good stress loading path. But as soon as we see some particle inside the soil domain undergo plastic deformation, our loading path are slightly deviated from the expected loading path. But this is very common and is attributed to the structural failure. On the other hand, if you're looking at on the pie plane, as you can see here, with the new boundary condition, we actually impose exactly the triaxial loading condition, right? So this is the expected outcome. And you can see how we actually using a very simple approach in SPH to impose the confining boundary stress condition in SPH, okay? For detail of this work, you can refer to our work published in NAC last year. Now, the other issue I also want to discuss related to SPH is the dissipative term. Obviously, if you're looking at this SPH motion equation here, you see that this equation are actually a fully dynamic equation. It's fully dynamic equation, especially when you're looking at when simulating the elastic material where you don't have any dissipative term in the dissipation mechanism in the concept model, then this equation are subjected to full vibration. And in the absence of any dissipative term here, the particle in the simulation will subject to free oscillation due to the unbalanced forces. And as a result, some sort of the dissipative term are required. And the most commonly used dissipative term are actually proposed by Monaghan's, which basically added into the motion equation. And this is the dissipative term actually formulated by Monaghan. And if you're looking at this dissipative term here, they actually simulate what? They actually approximate the fluid viscosity. Keep in mind that Monaghan actually proposed this term for fluid mechanics application and also astrophysics application, and therefore they approximate the fluid viscosity, which is correct because this term here, divergence of velocity, is corresponding to this term in the SPH, right? So as a result, when you're actually using this Monaghan equation of the dissipative term, you actually introduce the shear stress into the soil or shear viscosity into the soil, and therefore the larger amount of the viscosity introduced into the momentum equation, the more dissipation energy you would expect it. But the other good thing of this dissipative term, they actually smear across the kernel because of this summation. So it actually helps to remove the numerical oscillation. It actually conserves both linear and angular momentum because of the pairwise interaction, and because it actually acting in the reverse direction to the velocity, and as a result, they actually replicate the Rayleigh damping or damping coefficient, the damping force that we normally use in the continuum mechanics. Now, to give you an idea of how this term works, this is an example of the SPH simulation with and without the dissipative terms. Now, on the left-hand side here is the simulation without dissipative term, and on the right-hand side is the simulation with the dissipative term. And you can see that the numerical oscillation actually occurs when you are not using dissipative term. On the other hand, when you are using the dissipative term on the right-hand side equation, you was able to remove the stress oscillation. On the other hand, you still having the issue related to what Monaghan called shock length scale noise, which is basically related to the SPH summation. And the question here is, can we remove this stress noise? And the answer is yes, we can actually remove this stress noise by a very simple technique. For example, if you want to remove this stress noise to please the eyes, what you can do is you can using what we call the stress regularization techniques, like what we did here. So by using this, what we do is we applying this stress filtering to every SPH particle after several cycle of computation, and you should be able to obtain this sort of the result, which look very nice. On the other hand, even they look please the eye, but they actually not produce significant result compared to the traditional methods. The shock length scale noise here is very standard in SPH, and it will not produce any issue in SPH simulation because the SPH itself is actually the summation approach, and therefore the noise would compensate itself within the SPH summation. And therefore, even though the result that we obtain on the right-hand side look very nice, but it does not actually produce any significant difference compared to the one on the left-hand side. But this actually raises another question is, can we actually replace the artificial viscosity? Because this artificial viscosity proposed by Monaghan for the viscous fluid to simulate the viscous shear stress. But when we apply to the soil, we don't actually have anything that linked to the material property, right? So this is more or less the term that is designed by a trial and error sort of approach. So what we want to do now is we want to replace this term by something else, which is having more physical meaning of the classical damping in the solid mechanics. So what we can do is, if you're looking at the stress regularization technique, you can see that without using any dissipative terms, right? We can still produce a good result with the stress regularization technique that we presented here. But this is a result without any stress regularization technique. But the only issue here is we actually over predicting the runout distance of the granular material. And this is the issue of not having a damping force. And to avoid this problem, what we can do something very simple. We can actually replace the artificial viscosity by a kind of Rayleigh damping force, which is very similar to the damping force that we commonly use in the solid mechanics. This is damping coefficient, this is the velocity, and the damping coefficient here is linked to the material property, right? And by using this, we was able to again obtain the result which are very similar to the experiments like what you can see from here. This is the result on the left-hand side. You see the numerical result with Rayleigh damping. On the right-hand side, you see the simulation result without Rayleigh damping. And this is the reason why we can conclude here that we can actually reformulate the artificial viscosity by a very simple form like what we use here. But the issue of this is, this one is not good as compared to the artificial viscosity because it actually linked directly to the particle. It does not have to smear out the straight wave like what you can see from here. On the right hand side, you're still seeing some sort of straight wave which was not be able to damp out by this dissipative term, and therefore some better approach may need to formulate to remove this sort of wave propagation in the computational domains. So here, apart from that, this Rayleigh damping actually produce quite good result. For example, like what you can see from this result, this simulation result showing the result with the Rayleigh damping, and here we have the red line represent experimental result, the green line represent the numerical simulation using artificial viscosity, and you can see that both approaches are actually produce quite nice kinematic of granular flow without any problem. So this is the advantage of this approach. Of course, further advanced may need to require to remove the stress wave in the material. All right, the last aspect, I think. How long do I have, Manolo? How much time do I have?
Yeah, I think it is until 11:20. But if
11:20, okay.
To allocate some time for questions, that would be fine.
Okay.
So look, you are the boss, okay?
Thank you. Yeah, I think I'm finishing very soon, probably in 10 minutes. Yeah.
Excellent.
Yeah. All right. Thank you. Now, the last topic I would like to touch the base here is the constitutive model in SPS. And I'm not going to go into the detail of this because I believe that we're going to have an excellent lecture by Professor Wei Gu in the next lecture talking about constitutive model of fast granular material. But here, when you do actually working on SPS, it's very important to understand how what option do we have in terms of constitutive model. Now, SPS is basically the continuum numerical methods, very similar to FEM, except that the way we approximate the governing equation are different. And as a result, the SPS method actually share the same material constitutive model with the FEM, right? It's exactly the same, meaning that any existing constitutive model or straight return mapping algorithm developed for FEM can be simply adopted in SPS without any modification. So this is the good thing. Now, this is the generic constitutive model that we are using in SPS, and the constitutive model are written for each SPS particle or each RVE point. Okay, this is the key. And keep in mind that when you are using developing constitutive model for SPS, because we are dealing with a large strain problem, you need to adopt the Chorman stress rate to keep the stress objective to the rigid body motion. But this is still not a very rigorous approach. The more rigorous approach would be to adopt this finite deformation theory. But again, this is not something I want to discuss in this lecture. And here is a range of constitutive model that we can, and we have been successful to implement it in SPS, ranging from very simple elastic to perfectly plastic or softening material, or even damage and fracture. That's something we discussed in the next lecture. The issue that we are working with SPS is we don't have element tests. This is the most critical issue. When you implement a constitutive model in SPS, you don't know whether you are actually implement the constitutive model correctly or not. In FEM, you have element tests. You can use one single element, FEM element, to check your constitutive model, right? You can actually load the model, the element in different loading conditions to check, to test the constitutive model. But in SPS, we don't have. So what can we do? What they can do here is, and we have been quite successful in our research, is to using this what we call element test in SPS to check the concept model. So what we're doing here is when you implement a concept model in SPS, if you want to check the performance of concept model in your code, you can actually produce or create a computational domain like this, like what we have here. And then you're going to design the center area at the area where you allow the particle to freely move, while the outer area here will be the area where you impose the shearing velocity. And this condition here are corresponding to constant volume shearing. And this is an example of what we achieved with the very simple more column or tracker plugger concept model, elastic perfectly plastic concept model with different confining stress. For example, what you're doing here is you can actually sharing the soil under different confining stress, right? And then you can actually calculate the average or the sum of all stress of particles within this area here, okay? And then you plot the stress-strain relationship. This is a stress-strain relationship. And then you see that for the elastic perfectly plastic concept model, you should actually having this sort of behavior, right? Elastic and perfectly plastic. And in terms of the stress loading path, you should start from the confining stress and go straight upward until you're reaching the U surface. And you should stay here because this is the elastic perfectly plastic. And of course, the analytical result here can be obtained by using a concept level test. Okay, this is a very simple way to test a concept model, and this is the very simple concept model as well. You can also test using the same concept here to test a quite complex concept model. For example, what we're doing here is we're checking for the critical state concept model. And for this critical state concept model, we're actually looking at the material with different states, dense, mediums, and loose. And you can see here that we can even testing the behavior of material when they actually undergoes the liquefaction behavior. And one of the important aspects that you need to keep an eye in this element test here is that when you're testing sharing the soil, you need to make sure that there's no structural failure occur in your test, right? Otherwise, you would not be able to obtain a correct solution. And this is, again, you can see the very good kind of the element test in SPS, which I believe that if you are working on SPS, I would like to see more of this sort of application when you are submitting paper, because in many cases, when I review the SPS paper, many other papers are actually undermining this important component and ignoring whether they actually implement the concept model in SPS or not. When it comes to the prediction, you can see that if you actually correctly implement a concept model in SPS, you would expecting a good prediction. For example, here, you should be able to predict a very similar result to FEM for small deformation problem, of course. And in this case here, we compare the finite element solution with the Plaxis, SPS with Plaxis for small deformation problem. And you can see that the SPS could produce the result to a very good order accuracy to the Plaxis 15 node here, which is the high order accuracy elements. You can also be able to simulate the problem like what you can see here for granular flows, 2D and 3D, with matching very well with the experiments. Or you can even actually, if you ensure that your concept model works, you should be able to simulate this very interesting problem. For example, in this particular case, we can simulate the behavior of granular material under different states, right? So you can see that you can behave how they are different from the loose to medium and dense state. And this was a work conducted by one of my current PhD students. And or the other application, which is also highlight the need of SPS here, is the problem related to last deformation or excavation problem. In this particular case here, where we're trying to test the performance of SPS, so we're simulating the experiment conducted by Ito in 2009. And what you can see here is they actually excavate the soil, and they're having a number of instrumentation here to actually measure the soil deformation and when actually the slope is going to collapse. And this is the case where you can see that the SPS can predict fairly well the location where the slope is collapsed, unlike the finite elements where you actually continues you predict actually continuous deformation without any collapse. Okay. Now, different from the elastic concept model that I discussed earlier, we also have a different option in SPH to model what we call debris flows, right? In this case, the stress tensor we require for a momentum equation are formulated different. They actually following the computation of fluid dynamic approach, right? Where the pressure can be calculated by a stiff equation, which is a function of density, and the viscous shear stress can be calculated following the rheology model, which is again following the traditional computation of fluid dynamic approach. And here's a couple of options for the pressure equation. For example, Monahan in 1994, when he first expanding the SPH method for simulate the free surface problem of water, he actually formulated the equation which can be obtained by imposing the condition of 1% density variation. Or Morris actually proposed the equation which again calculate the pressure as a function of density, where C is the surface speed in the water. And I actually propose a very simple equation based on the compression test, which basically telling that the pressure can be calculated from the bulk modulus and also a function of density, where this equation has been tested to work with the soil in 2006. And in terms of the viscous stress component that we can have here, you have the option of using the Bingham fluid model, where you can actually introducing the shear strength of material, which is more column failure criteria, to the Bingham fluid, right? And this is the relationship between the viscous stress, where you have this is the effective viscosity, and this is the shear strain rate, and this is the viscous stress. And similarly, if you are dealing with a very fast granular material, you can actually using a very well-known rheology model proposed by Prof, which is telling you that the viscosity now is a function of the initial number and also the pressure dependent behavior. And here's a couple of examples. The last example that I would like to show. This is the comparison of SPH model using some side of the rheology model, and this was conducted by one of my master students. And you can see that using the rheology model, MUI model here, we can predict very well the runout distance and comparable result between the elastoplatis model with the MUI model, like what you can see from here, comparison between MUI and DP model. But when it comes to prediction of the stress, right, the stress profile, now you can see the clear distinction. With the DP model, we will be able to capture this sort of the arching stress in the granular material, like what you can see very clear here. You have the experimental data and you have the SPH result, and the SPH was able to predict very nice the arching stress in the granular material. But with the MUI model, you was not be able to capture this behavior. You capture something like this, like that's why you're actually having this form. You're actually predicting the parabolic shape of the stress distribution. So this is some sort of the comparison that we reported in our recent publication in Computer and Geotechnics. So with this, I would like to end my presentation on the fundamental aspect of SPS. I think I'm on time, I think. So this is the key conclusion that I want to make. First of all, is the SPS method is quite powerful tools to simulate the field scale problem, right? It's more targeted to large deformation and port failure problem. It also applicable and also have a potential to model the multiphase, multiphysical process that I'm going to explain in the next lecture. But keep in mind that when you are looking at something for small deformation, FEM is still the best option, and don't try the USPS for some small deformation problem. In this lecture, I also discussed some fundamental aspect of SPS, and I hope I have cleared some existing misconception on the concept as well as the capability of the methods. And my key conclusion from this lecture is it's very important to understand the key concept of SPS, some of its advantage and its disadvantage, because sometimes the disadvantage feature might become a very useful tool to actually obtain some purpose or some numerical purposes. So with it, I would like to thank you for your attention.